Hi, everybody. This is Miss Weeson, and this is the fourth podcast in Unit 1. Right now, we are about midway down on page 8, and today we are going to learn about electron configuration. Now, you might remember this when you were in honors chemistry. And actually, electron configuration is part of a much larger concept centered around something we call quantum mechanics. But for purposes of time, especially this year, we're not going to get into the nitty-gritty or the details of quantum mechanics, which ultimately tells you not how to do electron configuration, but why electron configuration is what it is. Now, I would encourage you in higher level classes, science classes in college, you will learn a little bit about quantum mechanics depending on your degree and where you're going. But it's not going to be assessed on the test in May. And therefore, we're not going to cover it here. Now, if we do have time at the end of the year, it is possible that we can come back to this. One of the things that I remember about electron configuration when I was in high school is we used a series of diagrams and orbital charts to do electron configuration. And I think before we begin, we should just kind of review the structure of an atom. And you could see here, this atom is probably exactly how you remember it from first year chemistry. And this model, we actually contributed to Niels Bohr. So this is what we would call the Bohr model of the atom. And again, it's just a quick review. You know that we have this dense central nucleus that contains the positive protons, as well as the neutrons, which are neutral in charge. And then floating around this nucleus, oftentimes we think in concentric circles or in rings or shells or orbitals that go further and further out from the nucleus are these negative electrons. Now, it's the negative electrons and the positive nucleus that provide that electrostatic connection to hold these atoms together. And before moving on to electron configuration, I need you to review some vocabulary from first year chemistry that we are going to consistently use here throughout the year, and that is a valence electron. So what is valence? Outermost. So the outermost shell would be the valence shell, and therefore it would house the valence electrons. Anything that is not considered the valence shell, we would call it core or core electrons. So any electrons that are not on the valence shell are referred to as core electrons. All right. So let's go ahead and take a look at another image of an atom. It's going to look slightly different, but it's ultimately the same. And give it a second. Okay. And this is called the Aufbau diagram. Hopefully what you can see here is that this image is an atom cut in half. And before we go on to electron configuration, let's just get into some theory here of what's happening. So where I've highlighted yellow is my nucleus. And what's going to happen in any atom, electrons are going to come in and literally fill an atom. And when they start to fill in orbitals, they're going to do so in such a way that occupies the lowest energy state first. They call this the ground state. It's the state that is the most stable, okay? And once that shell is filled, then electrons are going to move out to the next shell and fill that shell. Once that shell is filled, you can make a guess and probably say that the next shell will then start to take on electrons. You can almost think of this as a concert. You know, you want to fill everybody in on the first row. Once the first row is full, you want to get in on the second row, so on and so forth. And so when electrons are closest to the nucleus, they have their lowest energy state, but they also have the strongest affinity to the positive nucleus. So that connection between that ground state electron or electrons closer to the nucleus are going to have that really strong electrostatic connection. Now, as electrons start filling shells further and further away from the nucleus, then it's easy to understand that the connection or the electrostatic force between electrons further away from the nucleus starts to decrease. Now, interestingly enough, electrons can actually move from one orbital or shell to another. And there's a couple of ways that this can happen. You can excite the sample of atoms. You can bombard it with electromagnetic radiation. You could do a variety of things to excite the electrons within these atoms. And that's actually what quantum mechanics studies. It studies the behavior and the nature of these electrons and how they behave within atoms. So before we move on really quick to electron configuration, I wanted to lay out and point an interesting fact here that an electron, and I'm going to go ahead and just draw it as a red dot, okay, over this black, over the black one. If an electron is sitting in a lower energy state or a state closer to the nucleus and it becomes excited, it can actually jump to a higher energy level. So when we go from lower to higher, what do you think needs to happen in order to allow the electron to move further away from the nucleus? Well, if you said that you're going to need energy, you are absolutely right. In fact, because that force of that electron is so attracted to the nucleus, to overcome the force of attraction so that electron can move to a higher energy state or to a orbital further away from the nucleus. It's also true that an electron can go from a higher energy state and fall back to a lower energy state or to a place closer to the nucleus. Now, when this happens, energy is actually given off, okay? We actually release a quantum of energy called a photon here, okay? A photon. And you'll see this kind of referred to in the notes. Now, a photon of energy is literally kind of a little packet of electromagnetic radiation that's released. But let's get into the nitty-gritty and talk about how we actually do electron configuration. Now, I've embedded an extra PowerPoint, or excuse me, I've embedded here an extra periodic table that probably looks common. And what you see here is it's color-coded based off of the different groups. So the alkali metals, which is group 1. You've got the alkaline earth metals, which is group 2. You've got the transition metals, which is that entire inner block. You've got the noble gases over here. You've got halogens over here. You've got the lanthanide and actinide series down here. And that's what this color coding is coming from. When we do electron configuration, I'm actually going to annotate my periodic table in a different way and kind of look at it differently. And so here, what I'm going to do is I'm going to actually move helium, so you guys can see helium over here. I'm going to take helium over here, and for purposes of electron configuration, I'm going to move it right here, okay? So let's go ahead and just add helium there. So it turns out the periodic table is a tremendous tool for being able to do and to construct electron configuration. And the reason for that is because the periodic table, it's organized in a way that lines up with how the electrons are actually distributed in atoms. As you move over on the periodic table, so if you start at 1, you're adding an additional proton and electron as you go across the periodic table. So what we're going to do is we're going to outline 4 parts of the periodic table, and we'll call this our electron configuration periodic table. And so let me try to do a couple of colors here. In this first color, for the first block, I'm going to highlight in red. So we're going to call this block the S block. Let's go ahead and jump across. And what you're going to do is you're going to take this whole area, boron, all the way over to neon, straight on down. Remember, we moved helium over, so helium doesn't count over here. This is called the P block, or the P region, okay? And let's go pick another color. Let's do purple. Go ahead and take a third color. If you have a periodic table, you can just annotate the one on your handout that you've been given in class if you'd like to, or you can print up your own. Let's go ahead and label this one the D block. And let's do our last color. Let's go with, I don't know, orange. And let's go down to the lanthanide and actinide series and box that out and designate this as the F block, okay? So let's do a few examples to give you the idea of how this works. Let's go ahead and let's do carbon. Let's do a carbon's electron configuration. And so I'm just going to go ahead and write the electron configuration at the top of the periodic table. Now, here's the one thing that you need to understand. Over here on the left-hand side of the periodic table, you'll see 1, 2, 3 all the way through 7. Now, those are the periods or the rows of the periodic table. So we could easily do the electron configuration if we actually understand that there are 7 rows as well as an S, P, D, and F blocks. So let's go ahead and do carbon. What we're going to do is literally count every box, starting with the first one, which is hydrogen, until we get to carbon, which is the 6th element. So now what I'm going to do is I'm going to count every box, and the way I'm going to do it is like this. So I'm going to start in the first row, 1. So I'm going to write 1. And remember, I'm counting up to carbon, so I have to count hydrogen and helium, and those are in the S block. So I'm going to write S. And I counted off 1, 2 in the S block. So I'm going to put a 2 up here. Okay, now we're going to go down to the second row. Okay, so I'm going to put a 2 over here. And we're going to count off 1, 2, lithium and beryllium. Those are also in the S block. So you're going to do 2, S, 2. That 2 comes from you counting them off. And now, skirt on over, all the way over here. We now are still in row 2, but now we're in the P block. So I'm going to write 2P, and then go ahead and count over how many? Boron and carbon. That was 2, right? So your electron configuration for carbon is 1s2, 2s2, 2p2. Now, carbon is atomic number 6, meaning it's got 6 protons and 6 electrons. If you add up all the subscripts in the electron configuration, if you add up all the superscripts in the electron configuration, you should get 6, which is the atomic number, but most importantly, it designates how many electrons there are. So let's go ahead and do another one. Let's go ahead and do sulfur. Okay, sulfur. So we're going to do just like what we had done before. Let me go ahead and clean this up for you guys. We're going to start from the very beginning, which is in row number 1 at hydrogen. We're in the S block. Remember, I keep erasing helium, sorry. So helium's over in the S block, remember. So you've got 1, 2, 1s2, and it's S because you're in the S block, and it's 2 because you're counting them off, and you've run out of elements in the S block. Now we're done with the first row. Let's go down to the second row. So now we're in 2. We're counting off lithium and beryllium, and those are in the S block, and there's 2 of those. Hop on over to the P block. We're still in row 2, but now we're in the P block, and we're literally counting to sulfur. So we have 1, 2, 3, 4, 5, 6. So your superscript here will be 6. Now we got to go down to the next row, which is row 3. So you're going to write a 3 here. Count off sodium and magnesium, which are in the S block. So 3S, and that was 2 of them. Pop on over here to the P block. Now you're still in the third row. So 3P, and then you'll count off until you get to sulfur. 1, 2, 3, 4. 3P4. Okay. Are you kind of getting the hang of it there? Let's go ahead and do a little bit more of a complex one. Let's do a bromine. I'm going to go ahead and circle it on the periodic table. Let me erase this other stuff here for you so it's not too... All right, let's do bromine. Now here is something you need to know. The D block. The D block is always going to be one level behind the row it is in. So let me show you. Let's start off with bromine. I'm going to go kind of quick here. I'm going to pick it up, start from the very beginning. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, now we're on the fourth row. So you'd say 4s, 1, 2, 2. Now you are at the D block. Right here at the beginning where scandium is, remember the D block will always be one lower in the row than the row it's in. So it's in the fourth row, but since it's one lower, you're going to write 3D. And remember, we're going all the way to bromine, so count all the way to bromine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your superscript will be 10. Now the P block is not one level behind. So now we're at gallium, and we're back at the P block. But the P block is not one level behind. It is on par and in order with the row it's in. So 4, and then you're in the P block. 1, 2, 3, 4, 5. 4P5. All right, you guys. Now I will make one other note here. So go ahead and copy this into your notes. The D block is 1 level behind. And make the note that the F block, you guys, is 2 levels behind. We need to probably do a couple of more complex examples, and I'm going to actually give you right now, to finish this video up, I'm going to actually show you a short-handed way to do electron configuration. As you can quickly tell when we did bromine, your electron configurations can get really long. So really quick, we're going to learn how to shorthand notation. And so let's go ahead and go back to our notes. And now we're going to be back at the top of page 11. And there we go, it's loading. Oh, and I guess before we get on to do more examples, I just want to explain what I have here. You saw on the periodic table that we just annotated with electron configuration blocks or orbitals. You can see here I put a small diagram into the notes today, just to generally show you that the S, P, D, and F are actually atomic orbitals. They're literally three-dimensional spaces around the nucleus of an atom, and they are where the electrons are being housed. You can see that as you start to get into these larger ones, so really quick, this would be the S atomic orbital or molecular orbital. There'd be 3 P's, there are 5 D orbitals, and 7 F orbitals. Now it's a little bit more complex than this, and you can see that as we start to get into the larger atoms that have electrons in the D and F orbitals, there's a lot of overlap there going on. And then over here, there is a diagram. It's called an Aufbau diagram. It literally means to build up. And maybe you kind of saw us when we were doing electron configuration beforehand, we were using the periodic table to build the electron configuration of a particular element. So again, these diagrams are helpful, but not necessary. Before I move on and do a couple of practice problems, just wanted to mention to you guys that electron configuration is actually are actually concepts covered in more detail in first-year chemistry. And one more time, quantum numbers will not be assessed on the AP exam. Okay, let's do a couple of examples. I put the element number next to each one. So I have argon, vanadium, barium, and mercury. And I will do one quick review with argon, and then I will show you how to shorthand. And then I'm going to ask that you please, I'm going to scroll down really quick. And then I ask that you please do exercise 14 on your own. One big hint before I forget to say anything is in exercise 14, you have ions. So look at D and E. You have a cation and an anion. And so yes, you can do the electron configuration for ions. Now, I want you to try the electron configurations of these elements. We will talk about them a little bit more in class. More specifically, I'd like to do those D and E in class. Okay, let's go back up and do argon. Now, I guess the easiest thing for me to do would be go back to the periodic table that I was annotating, so you guys have a visual reference. And give me just a sec while I erase. Okay, so I cleaned up the periodic table a little bit more. I apologize for the kind of sloppiness, you guys. And again, we're going to do argon. So let's go ahead and circle it. And remember our electron configuration. I'm going to do it the long way, and then I'm going to show you the shorthand notation. Remember, when we do electron configuration, we're going to count up to argon, starting at the very beginning, which is hydrogen. After I'm done doing the longhand notation, I will show you the shorthand notation, which is perfectly acceptable for you to do on your learning checks, your exams, and even the AP exam in May. You can definitely do shorthand notation. So let's go ahead and do argon. Okay, you're going to start over here, and you are in the first row. Okay, and so it would be 1. You're going to count hydrogen and helium, and those are both in the S block, and you've counted off 1, 2 of them, so your superscript will be 2. And that is it for the first row. So now we're going to go to the second row. So now you write a 2. you're going to count off lithium and beryllium, and you counted off two different elements that are both in the S block. So you will put a two superscript there. Now we head on over to the P block. And so you're still in the second row. So I write 2P, count off all the elements, 1, 2, 3, 4, 5, 6, all the elements there in that P block. And there were 6 of them, so you put the 6 superscript. Now we go down to the third row and we count off sodium and magnesium. We counted off 2 in the S block, so it would be 3S2. Go ahead and count on over all the way to argon in the P block now. 1, 2, 3, 4, 5, 6. We're still in the third row. We're in the P block and we counted off 6. So that's the electron configuration for argon. But if you didn't want to spend your time doing all of that, the shorthand notation basically states this, that whatever element you are writing the electron configuration for, that you would find the noble gas that comes before it. So right now, argon is obviously a noble gas, but we need to refer to the noble gas before it. And so obviously the noble gas that comes before it is neon. So what you then would do is you would put in bracket neon, and then you would literally pick up your electron configuration after that noble gas. So in this case, we are now on the third row, S2, 3P6. Okay, so that is shorthand notation. I'm going to go ahead and do one more example for time's sake so you guys don't have to listen to me in a long podcast here. Let's go ahead and do vanadium. So I'm going to circle it on the periodic table. It's element number 23. Let me go ahead and clean things up for you here. All right. Now, because you're getting the hang of electron configuration, I'm going to do it longhand, and then I'll do noble gas configuration, which is the shorthand. Okay, so I'm going to go pretty quick here. 1s2, 2s2, 2p6, 3s2, 3p6. I'm now in the fourth row, so 4s2. Remember, after we're done, after we get to calcium and move over to scandium, we are entering the D block, or the transition metals. And what this means is that the D block is going to be one level behind. Even though it's in the fourth row or in the fourth level, it's one level behind. Again, why this is, we can explain in more detail if you'd like in class, but that's what's happening here. So you're going to go back down to 3. You're in the D orbital, so you're going to write 3D, and you literally count over 1, 2, 3. So here is your electron configuration for vanadium. How do you do shorthand noble gas configuration? Identify the noble gas that comes directly before vanadium, and that would be, let's highlight it on the periodic table, that would be argon. So you will bracket argon and pick up your electron configuration from there. So it'd be 4s2, 3d3. Okay, you guys, I want you to try the rest of the examples in the notes. I think there's 2 more, barium and mercury, and then I want you to try exercise 14 on your own, and we will be going over them in class. Thank you.